Alright, now it's time to talk about intermolecular forces. So with this unit, we're going to look at the forces in between individual molecules. And that's what the word inter means. So intermolecular forces means it's forces between two separate molecules. Now, the mix-up that students tend to have in this unit is the difference between intermolecular forces and intramolecular forces. Intramolecular forces we've talked about a lot. That's just a fancy way of saying bonds. So covalent bonds, ionic bonds are all intramolecular forces. So a good way to think of those is just the forces within. So if you're looking at a molecule, the forces that are holding that molecule together with itself would be the intramolecular forces. Covalent bonds, ionic bonds. Intermolecular forces, though, would be forces between two separate molecules. So here's something I need you to get right now. So maybe say it to yourself a couple times before you go to bed. Repeat it over and over again at the dinner table. Intramolecular forces are what hold molecules together. So if we have something like this is methane. Right now, there is only intramolecular forces at play. It's the covalent bonds that are holding this together. There is no intermolecular forces. Why not? Because there is no other molecules here. Intermolecular forces are forces between molecules. So if we were to throw another methane in here, so now we have two methane molecules, now we're going to generate intermolecular forces. So my intramolecular forces holding this together, intermolecular forces would be the forces between these two guys right here. So if you have a single molecule, you cannot have intermolecular forces. You have to have a plethora or multiple molecules. So here it is with water. Intramolecular forces. So each of these water molecules have their own individual intramolecular forces, the covalent bonds that are holding the hydrogens and the oxygens together. They also, if we have two of them like this, we have intermolecular forces, which are forces between these two molecules, and they're forces of attraction that pull them together. Now, if we didn't have this water molecule right here, we would not have intramolecular or intermolecular forces because there would be nothing to attract this one to. Now, intramolecular forces are significantly stronger than intermolecular forces. They're what hold the molecules together. Intermolecular forces, while they're much weaker, do have a lot of play on characteristics of molecules, so boiling points, melting points, and how they arrange themselves in a structure. So we're going to go through in this video and talk about the different types of intermolecular forces. And keeping in mind, when we talk about these, we're talking about forces between two or more molecules. Before we progress any farther, we need to go back and talk about something that we looked at a little bit back with Vesper, and that was dipoles. So we think about molecules and polarity. So in this case, we know that oxygen is more electronegative than hydrogen. So that means the electrons are going to be pulled towards the oxygen, which means we will have an area up here of higher electron density, which essentially just means the electrons are spending more time up here than they are down there. As a result of more electron time up there, we're going to wind up with a slightly negative charge up here. And that's what we call a dipole. So a dipole is a slight or partial charge that's created due to polarity. And since those electrons are spending more time up here, that means they're spending less time down here, which means down on this side, we're going to have dipole positives. So we'd have a negative region and a positive region. That's what generates dipoles. That's what generates polarity. So then our first intermolecular forces would be the ion dipole IMF. So these are the forces of attraction between an ion and a polar molecule. So right here, these circles represent polar molecules. They've got their negative region and their positive region. So like on a water, this would be the oxygens, this would be the hydrogens. And then we have a cation and an anion. So if we have salt water, when we put salt in water, it's going to decompose, or it's going to ionize into sodiums, so Na pluses, and Cl minuses. And so then the water, which is also polar, has that negative in the positive region, is going to arrange itself around those positives and around those negatives. So the negative oxygens on the water would be attracted to the positive sodiums, and the positive hydrogens are going to be attracted to the negative chlorines. And so what we get then is a force that's going to hold these guys together, and that would be an intermolecular forces, because it's the force between these two molecules. And this is why when we put salt in water, it disappears from our sight, because the water molecules break apart those sodiums and the chlorines and surround them, so that they're just individual cations and anions that we can no longer see. And what holds those sodiums in there is going to be the intermolecular forces here. Things that aren't soluble in water are going to be things that water is not going to be attracted to and create those intermolecular forces that cause it to disappear. So if you think of like oil. oil is not soluble in water because it does not create any intermolecular forces. So here's a pictorial of the sodium chloride in water. And so if we imagine this, then the sodium or the waters aren't just going to be surrounding on the sides like that. They'll be surrounding three-dimensionally, so all around. This process is called solvation, then, when the water molecules surround ions. And then what's holding these guys together is going to be, of course, the intermolecular forces. And the intermolecular forces that are holding these together are going to be the ion-dipole intermolecular force. So let's take this opportunity to bring Coulombs Law back into play. So remember, Coulombs Law is a force between two opposite charged molecules, or opposite charged atoms, and it's dealt with the distance and then the charge of the atoms. So the farther they are apart, the lower this force is going to be, or the stronger the charge is, the higher that force will be. And if we think of the solubility rules, not all ionic compounds are soluble in water. And the reason for that is intermolecular forces versus Coulombs Law. So if the dipole charges on water aren't strong enough to break apart ions, a particular ionic compound will not dissolve. So the ionic compounds that don't dissolve are ones where the Coulombic attraction is going to be greater than the ion-dipole attraction. So as a result, the ions stay together, and they do not come apart in the water, so therefore they do not dissolve, do not disappear from our sight. But something like sodium chloride, where there's going to be a large distance between the two centers, and then the charges of them aren't that great, it's going to be a fairly low Coulombic attraction, and so therefore the water molecules are able to break that apart. So if you're thinking magnesium hydroxide versus barium hydroxide, magnesium atoms are going to be a lot smaller than barium are because of that extra row of electrons. And so as a result then, our distance is going to be less in this case, which means our force is going to go up. Water is not able to break apart that force, and so magnesium hydroxide as a result is not soluble in water. Barium hydroxide, on the other hand, since the molecules are much larger, since the ions are much larger, you're going to have a lower force, and so water is able to break that apart. However, if we were to find a soluble form of magnesium, like magnesium chloride, its Coulombic attraction between the water molecules, so its intermolecular force, would actually be greater than it would for barium. And that's because magnesium, since it's smaller, same rule there, it's going to be the Coulombs Law, where the distance is shorter, so therefore the attraction would be greater. So the attraction for water molecules to magnesium would be greater than it is for barium to water. And also, if we were to put magnesium in water, you'd be able to surround more water molecules around it than you would barium, and so it's going to have a greater attraction there as well. So one last look at the ion-dipole ionic bonds. So the ion-dipole, the intermolecular forces here, are going to be trying to pull those two apart, but the ionic bonds are what's holding it together. So what makes something soluble is when this force, the pulling apart force from those water molecules, is greater than this force right here. All right, next in line for intermolecular forces is the dipole-dipole intermolecular force. So this is the attractive force between two polar molecules. So if we have two polar molecules like water and ethanol, they're going to have an attraction because they've got the positive and the negative regions that are going to attract each other. So if you have polar molecules that are together, solution, solid, gaseous, whatever it is, they're going to line each other up and attract each other, positive to negative. And so this is going to help hold those molecules together. If there was no force right there, no positive and negative holding it together, they would not really be attracted to each other, so they wouldn't interact with each other very much. And Coulombs Law still applies. The closer those two are together, the stronger the force is going to be. So here is what this would look like in a solid. So when molecules slow down and form into a solid, they're going to set up those intermolecular forces between the positive and negatives. So molecules will naturally arrange themselves just like this because the positives are going to repel each other, so they're going to separate, and you'd get the negatives and the positives lining up. And this creates a very rigid rectangular solid. And they minimize the repulsions and attempt to maximize the attractions that they have then. In a liquid, there's going to be a lot more moving around, mo heat, mo motion, so they're sliding around past each other, but they're still going to have those forces of attraction. So they're going to kind of arrange themselves to minimize those repulsions, maximize those attractions. So these forces are strong, but they're not strong enough to actually hold them in place. So once they get enough energy, they can break those intermolecular forces, but they're just going to reform. So like this positive right here might be attracted to that negative, but as it slides around, it might start attracting to that negative. And so you're going to be constantly moving around, changing forces, but always the forces are going to be there. Now, there's a special type of dipole-dipole bond, and that is the hydrogen bond. So the hydrogen bond It's not really a bond per se. It's not like a covalent bond where things are holding on. It's just an intermolecular force. So it's just going to be attraction between opposite charges. Hydrogen bond is a dipole-dipole bond. It's just an especially strong dipole-dipole bond. So if we have hydrogen that is covalently bonded to either fluorine, oxygen, or nitrogen, and then it's put in a solution or it's put together with another hydrogen that's covalently bonded to a fluorine, oxygen, or nitrogen, we're going to create a very, very strong intermolecular force that we call a hydrogen bond. Now, fluorine, oxygen, and nitrogen are the most electronegative elements on the periodic table, which means they have the ability to really pull the electrons away from hydrogen, thus creating a very, very strong partial negative or partial positive and partial negative. So since we have a very, very strong partial positive on that hydrogen, and we're going to have a very, very strong partial negative on the A's in this case, whatever it is, that means we're going to have a very, very strong intermolecular force. It's going to wind up being about 5 to 10 times stronger than any other dipole attraction. So there's a couple things in play. First off, we already said that fluorine, oxygen, and nitrogen are the most electronegative, so therefore it's going to be very, very polar bonds. But also, this is going to be extremely small. We're talking about hydrogen, which is the smallest of all elements, and then fluorine, oxygen, and nitrogen, which themselves aren't very large. So since they're very close together, we're going to get a strong difference in electronegativities. And it's going to be very, very concentrated on those particular atoms. Also, the lone pairs in the fluorine, oxygen, and nitrogen are going to increase those partial charges. So since we are bringing those electrons over to an area where there's already lone pairs, we're going to have an extremely negative area around those fluorines, oxygens, and nitrogens. And if you look at the Lewis structures, you can see this. So here we go, water molecules, perfect example of hydrogen bonds. The intermolecular forces between water molecules are extremely strong. That's why when you fill a glass all the way to the top, it kind of bubbles over and forms that skin. It's because of those intermolecular forces, those hydrogen bonds. Why little leaves can float on top of water. They're just sitting on that skin that's formed between those dipole forces. And so what's happening then, the electrons are more attracted to the more electronegative oxygens, thus creating those dipole negatives. And then we have that electron density up there, plus we have those lone pairs. So we've got a lot of electrons up there creating that negative charge. On the hydrogen then, hydrogen doesn't have any lone pairs. The electrons are pulled over towards this side. So it's going to be extremely positive down there in that region. And so these intermolecular forces hold the water molecules together and actually attribute a lot of the properties of water, like its boiling point, its structure when it freezes, the fact that it's got surface tension. And in a glass of water, there's going to be trillions upon trillions of these because all of the waters are going to be attracted to all of the other waters with these intermolecular forces. And once again, if we just had a single water molecule, we wouldn't have hydrogen bonding because there's no other water molecules for it to hydrogen bond to. And water doesn't just have to hydrogen bond to itself. It can hydrogen bond to other things. So something like methanol. Methanol is going to have that oxygen to hydrogen right there. And so that's going to create that hydrogen bonding. We're going to have the large electron density right there, low electron density there. And so we're going to generate all of those different hydrogen bonds. And if we consider a molecule like acetamide, acetamide's going to have hydrogen bonds, and those are generated because it's got the nitrogen to hydrogen in this case. That's going to generate that electron density. And so it's going to be able to attract the oxygens in this case on the other side that are going to have all those electrons, and so we're going to set up those intermolecular forces. Now, if you look here, acetamide is able to set up 2 intermolecular forces with itself, which is going to generate a very, very high boiling point then, because it's going to take a lot more energy to break these molecules apart from each other. And so its boiling point is even higher than water, because water's only got 1 intermolecular force. Also, these molecules are going to be significantly heavier. Since they're heavier, it's going to take a lot more energy to break them into the gaseous phase. Now, a molecule like ethanol does not form hydrogen bonds. A lot of students will look at this and say, well, it's got oxygen, it's got hydrogen, therefore it's going to form hydrogen bonds. It's not the case. The hydrogens have to be covalently bonded to either fluorine, oxygen, or nitrogen. In this case, the hydrogens are covalently bonded to the carbons, so it will not form intermolecular forces, or hydrogen bonds in this case. It'll form other intermolecular forces, just not dipoles. So with this chart, we can see the power that hydrogen bonds have on boiling points. So something like water molecules that have hydrogen bonds are going to have relatively higher boiling points than other molecules, like methane. Methane that has no intermolecular forces is going to have a boiling point less than 0 in the negative range. Ammonia, which is going to have hydrogen bonds, is going to have a high boiling point as well. And even though ammonia and water both have hydrogen bonds, not going to set up those hydrogen bonds. It's not the oxygen, nitrogen, or fluorine. It's other atoms that are bonded or covalently bonded to those hydrogens. So when we're relating this to boiling points, boiling point would be the point where molecules separate from a liquid, where they're pretty close together, intermolecular forces are doing some action, but then when we separate them into gaseous state, that means they go completely their own ways. And so we would consider intermolecular forces not really playing a role at that point. And so in order to boil something, you've got to put in enough energy to break those molecules completely apart. So if we consider something like water, okay, it's going to have low potential energy when it's just sitting in a liquid state because those molecules are going to be held together by those intermolecular forces. When we start to boil it, though, we're trying to break those bonds, which means a high potential energy. This is like lifting something up, or a rubber band. If we were to stretch it, the farther we stretch it, the more energy that has to be put in until the point where we can break apart completely and not have those forces holding it together. And so something that has strong intermolecular forces, it's going to take a high potential energy in order to break those intermolecular forces and cause it to boil. Now at this point it's worth mentioning that not all molecules are polar. You can have what's called a nonpolar molecule, so those would be the ones that do not have the dipoles. So this would be a good time to go back and review when we talked about bonding and stuff, and we looked at the different shapes, which ones generate nonpolar and polar molecules. So in the case of like methane, tetrahedral shape, it's got symmetry all around, and so this is going to be a nonpolar molecule. What that means is even though the electrons are naturally going to be pulled more towards the more electronegative carbon, since it's got that even distribution, the electron density is going to stay consistent throughout this entire molecule. As a result, you don't generate dipoles, so this would be a nonpolar molecule. If it's nonpolar, that means two methane molecules are not going to have those dipole-dipole intermolecular forces because there is no dipoles to attract each other. However, if we put a nonpolar species like methane next to a polar molecule, such as water, you can get what's called a dipole-induced dipole. So a polar molecule obviously has the dipole and positive and negative, and in a nonpolar species, it has the negative that's evenly distributed, so the electron density is the same throughout. However, if you put this polar molecule next to a nonpolar species, you're going to have a positive and a negative side. So that positive side right there is actually going to attract the electrons from this nonpolar species, which means the electrons are going to be pulled over this direction, creating what's called a polarized molecule. So that means at this point right here, since the electrons are pulled to this side, we're going to get an area with higher electron density and an area with lower electron density. What that is then is a dipole. And so we have a polar molecule that's inducing a dipole over here, creating a polarized molecule. As a result then, we get a weak intermolecular force between the polar and the induced polarized molecule. So if we think of something like dihydrogen sulfide, which is a polar molecule, it's got the bent structure, we're going to have more electron density over here on this side, so a higher electron density is going to generate that dipole negative, and then over here where we've got the lower electron density, we're going to have that dipole positive region, and this is going to be natural with this molecule, it's just due to the structure. Methane, on the other hand, though, because of its tetrahedral shape, its symmetrical orientation of all of the electrons means that all of the electron density is going to be evenly distributed throughout the molecule. So there is going to be no natural dipoles. However, when we bring these two molecules close enough to each other, see that slight positive charge right there? That's going to attract all the electrons on this methane and pull them to one side. So if it pulls them to one side, that means we're going to have an area of high electron density, a dipole negative. And then we're going to have an area over here of a low electron density, so a dipole positive. Now, this is not as strong of a polar area or a dipole negative as like this one would be. However, it's enough to induce an intermolecular force between those two. And so we're going to have a slight attraction between those two molecules as a result. This is going to be a much weaker bond than like a hydrogen bond or even a dipole-dipole bond. So a dipole-induced dipole bond is weak, but it's enough to kind of offer a little bit of attraction between these two molecules. So there's two factors that can affect dipole-induced dipoles. First off, molecules that have larger dipoles, so something like water that has hydrogen bonds, that means it's going to have very, very strong positive and negative regions. They're going to have a larger ability to induce a dipole in a nonpolar species. So that stronger positive charge or negative charge means it's going to be easier to induce a dipole in a nonpolar molecule. Also, larger nonpolar molecules are more polarizable, which means it's easier to have their electrons shifted to one side. And in that case, if you have a larger molecule, it's going to have a much stronger induced dipole. So if we're comparing the strength of dipole-induced dipoles between different molecules, we would look first at the magnitude of the dipoles, so if it's if it's got hydrogen bonding, and then also the size of the nonpolar species. So if it's a larger nonpolar species, it's going to have a greater strength of dipole-induced forces. And finally, we have the induced dipole forces. These are also known as the London dispersion forces. In fact, it's probably easier just to call them that. So these forces exist between all species. So no matter what we are talking about, you're going to get questions where they ask you, what intermolecular forces are at play here? You should always answer London dispersion forces. No matter what, they will always be a player. You might have other kinds. You might have hydrogen bonding. You might have polar or induced dipoles. But London dispersion forces is always going to be one of the answers. In completely nonpolar species, if we have two nonpolar species together, London dispersion forces will be the only intermolecular force at play. So anytime you're looking at nonpolar species that are together, it's only going to be London dispersion forces. And what they're caused by is just Coulombs Law, and it has to do with just kind of the natural shifting of electrons inducing dipoles in neighboring species, and therefore altering the electron distributions. So if we think of a nonpolar species, the electrons are going to be all around that nonpolar species, evenly distributed, and so therefore there's not going to be really those dipoles. However, electrons are constantly moving around. So as they're moving around, take a look at this. So just one point in time, 0.1 second, take a picture. Here's the electrons that just happen to be over on this side. Hey, what do you know? We've got a little dipole right here because electrons are just happen to be over there. And so we've got a region with more electron density just for an instantaneous point in time. Within another split second goes by, those electrons move around, and hey, look, now they're over there. Dipoles in a slight different place than they were before. And we can keep doing this as time goes on. We generate different dipoles in different areas, and since this is constantly changing. And really, if we consider this over time, that electron density is spread out so far that really it's spread completely out through the entire molecule, and so we generate this nonpolar species again. So on average, a species is going to be nonpolar, but on an instantaneous scale, it's going to have those dipoles. So this random movement of electrons causing dipoles is then going to induce dipoles in neighboring species. So let's consider this one right here as our starting point. So if the electrons are moving around and we take an instantaneous point in time, so right here the electrons are all dispersed or higher electron density right there. This is going to then repel the electrons from this guy and cause them to go to this side, thus giving us electron density. So we've got a negative and a positive region that are going to attract each other. Well, if all the electrons are pushed to this side on that species, that's going to push the electrons to that side on that one, and then push it to the electrons to that side on that one right there, creating this kind of intermolecular force, this London dispersion force that's going to hold these molecules together. But hey, time goes on, the electrons right here are just going to keep moving, and as they move over, what do you know, they're going to be a higher density right there, which is then going to shift the dipoles this way. And so these bonds are constantly breaking and reforming. This is going to be a very, very weak intermolecular force, but it's going to be an intermolecular force nonetheless. And so larger molecules are going to have their electrons more spread out. And if they're more spread out, it's easier to polarize. It's easier to pull those electrons to one side or the other. So if we look at this chart right here, boiling point is an indicator of intermolecular forces. So a higher boiling point means it has stronger intermolecular forces. So iodine, which is the largest of halogens, is going to have the highest boiling point. And that's because it's the largest species, and so it's going to be more polarizable, which means the iodine molecules are going to be held on more tightly to each other than bromine, chlorine, fluorine, and helium. And so that picture we saw in the last slide where the electrons can be shifted to one side or the other, it's going to be a lot easier to shift the electrons in iodine than it is in bromine. As a result, iodine has a higher boiling point. So this is due to the fact that the electrons are much, much farther away from the nucleus, so the effective nuclear charge is going to be weaker, and so those electrons are going to have a lot weaker of a hold to their center nucleus. And so as a result, it's going to be easier for neighboring molecules to pull its electrons to one side or the other. Two other things that play a role then in polarizability, along with size, pi bonds, which would be like double and triple bonds, are going to be more polarizable. That's because electrons are delocalized in the polar bond with a pi bond, and so they're going to have more ability to move, thus helping with polarizability. So molecules with pi bonds, with double or triple bonds, are usually more polarizable than ones with just single bonds. And then geometry also plays a role, so the shape. A molecule like this is going to be much more polarizable, and because we have kind of a flatter area right there. And so it's going to be easier for another molecule to come in here and shift the electrons away. as opposed to kind of a clunky, misshapen molecule like that. It's going to be harder to delocalize or de-shape the electrons in a molecule like this. So more linear or more geometrically shaped molecules are going to be more polarizable, and therefore have stronger London dispersion forces. Okay, here's a sequence that's going to be a general guide for determining which intermolecular forces are the strongest. Now, something to keep in mind here, this is only when we're comparing molecules of similar size. So, for example, ion-ion is the strongest, then ion-dipole, hydrogen bonds, dipole-dipole, induced dipole-dipole, and then dipole-induced dipole, and then finally London dispersion forces. However, if we have a very, very large molecule, London dispersion forces in a large molecule will be stronger than its hydrogen bonds or in its dipole-dipole bonds, even though it's lower on the scale. However, if we have smaller molecules or two similar sized molecules, hydrogen bonds, dipole-dipole would be stronger than London dispersion forces. And if we're comparing two different size molecules, so like iodine that's very large and it's only got London dispersion forces, and then water, which is significantly smaller, but it's got hydrogen bonds, and so hydrogen bonds are stronger, but the intermolecular forces in iodine are stronger than the hydrogen bonds in water. And that's because iodine is much larger, and so it's easily polarizable electrons are going to have stronger London dispersion forces than even the hydrogen bonds in water. So this scale is only relative for evenly sized molecules. If we compared, H2O to H2S, two molecules that are similar in size, well, water has hydrogen bonds, dihydrogen sulfide only has dipole-dipole, and so the intermolecular forces in water would be stronger than they are in hydrogen sulfide. So it's not always just as clear-cut as this scale right here. We do have to consider other factors.